So, the other day, I was walking around and I found this rock. And I was wondering, how did it come into being? I can tell that it is a sedimentary rock, but before I analyze it more than that, I should talk about some important geological features of sedimentary rocks, namely graded bedding, imbrication, ripple marks, flute casts, mud cracks, and stalactites. So, this rock has graded bedding, as you can see here, because the larger rocks are closer to the bottom and they slowly get smaller as you go up. This is often caused because a stream must be moving at faster speeds in order to transport larger rocks. So, the larger rocks get deposited first, and then the smaller rocks tend to be deposited on top of them. Next is imbrication. Imbrication means that all the clasts in a sedimentary rock are parallel to the flow of a stream. There are several types of imbrication, namely A-axis imbrication and AB plane imbrication. A-axis imbrication means that all of the clasts within a sedimentary rock are parallel to the flow of the stream in one line where they were deposited. As you can see, each of these rocks tilts this way. So, this is an example of imbrication. Because there is also a secondary plane here, where the rocks are also tilted in the same direction, this is an example of an AB plane imbrication. Next are ripple marks. They are given their name due to their similarity in appearance to ripples on disturbed water. They indicate agitation in the bed of the water due to wind, waves, or current. Much like ripples and waves indicate agitation on the surface of water, there are several types of ripple marks: straight, sinuous, catenary, linguoid, and lunate. There are sinuous ripple marks, which each flow in the same direction, but each mark appears to be curvy instead of straight, like on straight ripple marks. Sinuous ripple marks generate cross laminae, meaning they flow perpendicular to the stream, possibly due to the slowing of current. Catenary ripple marks look a lot like a repeated W. Like sinuous ripple marks, they also have cross laminae, and they are created by a dip in the flow of a body of water. Lastly are linguoid and lunate ripple marks. They are characterized by their random shape. The difference between these two types of ripple marks is that on linguoid ripple marks, the backside, or lee, of the ripple marks are curved, where on the lunate ripple marks, the front side, or strass, is curved. Here's an example of a flute cast. Flute casts are created when water digs holes into the soft mud in stream beds. After the stream beds have carved the holes, new, coarser sediment fills the newly created holes, which creates the flute casts. Each flute cast is aligned parallel to the current of the bodies of water. Flute casts also tend to be raindrop shaped, with the blunt end facing upstream, which tapers off as it heads further downstream. They can range anywhere between a couple of centimeters to a full meter in length. This is an example of a flute cast. Likely this would be the upstream side, as it's a little bit blunter and it tapers off down here. As you can see here, stalactites appear as jagged edges on a rock. They are created when minerals are dissolved from the larger rock outcropping in a process called pressure dissolution. Stalactites usually occur in homogeneous rocks such as chert, sandstone, and basalt, but they can also be found in ice. They can range anywhere in size from the microscopic to 20 meters in length and 10 meters in amplitude. In order to create a stalactite, there must be a solution in the rock and pores that can carry liquid to help dissolve the rock. Stalactites are usually formed parallel to the bedrock. Now, back to the rock I found. As you can see here again, this rock displays graded bedding, which is a marker of a sedimentary rock. This suggests that larger rocks were carried downstream and deposited here when the stream slowed down. These rocks are also on top of a soft, fine sediment. This could suggest these rocks were carried down after a large flood. We can tell the stream was flowing this way because the rocks here are imbricated like so. Different rocks are aligned here, here, and here, so we can tell there is some imbrication. The lower section of each of these clasts is the upstream side. In conclusion, this rock was created in a large flood event which swept many larger rocks downstream. But how fast was the water going? The largest cast on the rock is here. It is about 551 millimeters in length. So, using a Hillstrom diagram, a graph which depicts the size of a sediment versus the speed of water needed to move the sediment, we can determine that the water needed to be moving at 700 centimeters per second, or 7 meters per second, in order to pick up the rock, and 200 centimeters per second, or 2 meters per second, in order to redeposit it here. This is also roughly 16 miles per hour and 4.5 miles per hour respectively. In summary, this rock was created in the aftermath of a large flood event where boulders got swept downstream. Alright, that's all the time I have. See you next time when I discuss the next hot topic, igneous rocks.